Welcome, ladies and gentlemen, to a presentation about weather, the fundamental processes of weather, where we're going to be discussing what weather is, how weather works, where weather works, and a bunch of other cool stuff about weather. So what is weather? Weather is simply the state of the atmosphere, the layer of the gas that envelopes the Earth. Currently, the atmosphere is a conglomeration of many gases, of which 78% is nitrogen, 21% is oxygen, 0.9% is argon, and 0.03 is carbon dioxide. The remaining 0.07 is generally referred to as other gases, and it includes stuff like water vapor, of which the condensed form is clouds, hydrogen, the ozone that protects us from the harmful UV rays from the sun, and some other gases as well. The atmosphere, like everything else on Earth, is kept in place by gravity. The question that might arise is how can that be if air has such negligible weight? Well, yeah, in small amounts it's quite light, but the whole atmosphere together weighs 5.5 quadrillion tons. And that, ladies and gentlemen, is the cause of air pressure. Standing at sea level, the atmosphere exerts a pressure of 14.7 pounds against every square inch of the human. If you go below that, air pressure increases, and if you go above, it decreases. The more pressurized the air, the closer the molecules are packed together. That is why it's harder to breathe air at higher altitudes, where the molecules of oxygen are spaced further apart. And obviously, that means, of course, when you are lower, it's easier to breathe air because the molecules are closer together because of density. Hot and cold weather. It might be a strange concept to understand, but the sun is actually not what heats our atmosphere, or at least percentage-wise mostly. Generally, the water vapor and carbon dioxide molecules simply let the shortwave radiation from the sun pass them by, because it's too high frequency for them to absorb it. But once the solar radiation reaches the Earth and is absorbed in the Earth itself, the Earth emits its own radiation known as terrestrial radiation. Terrestrial radiation is in the form of long waves that are easy to absorb, hence the atmosphere is generally heated up by that. So technically, it is still the sun that does the job, but it's our planet that does the hard work of supplying our atmosphere with absorbable radiation. So there are four basic layers that the scientists divide the atmosphere in, and those layers are based on temperature. The troposphere is the innermost layer, and the layer that we're in currently. Even the highest mountains are under the boundaries of this layer. The troposphere is 11 kilometers above sea level. It contains all our weather and 80% of the planet's air mass. Additionally, it's the layer where the air pressure is highest. The stratosphere, the second layer, ends at 48 kilometers above the planet's surface and contains the ozone layer, the layer that protects us from the sun's harmful radiation, as discussed in the first slide. The mesosphere is the third layer. It is located more than 80 kilometers above Earth's surface. Here, temperatures decrease as low as minus 90 degrees Celsius. The thermosphere is the outermost layer of our atmosphere, and I'm not counting the exosphere which is generally referred to as the fifth layer, because it is not counted here since the air there is so thin that it is comparable to the airless void of outer space. This is the part that is actually heated by the sun, meaning the thermosphere, mainly due to the small mass of the molecules. Thus, the thermosphere is actually a warm region of the mesosphere. Now, if you think about it, the thermosphere gets heated, well, partially by the sun. The troposphere, as discussed in the previous slide, is heated by terrestrial radiation that leaves the mesosphere to be the coldest region of all. Hence the minus degrees Celsius that we discussed earlier. Okay, now let's discuss windy weather. This might get a bit windy here, so just hear me in on this. When air in the troposphere heats up due to terrestrial radiation, the molecules move around more rapidly, pushing each other further apart and becoming less dense. This less dense air then rises upwards towards thinner air until it cools and drops back down again. This happens because different parts of the globe are heated differently, and this difference in temperature causes difference in air pressure, which in turn causes wind. These are the three forces that dictate the power and the direction of wind. The pressure gradient force is the cause of cyclones, which are low pressure centers rapidly making their way up. High pressure gas then starts circling the cyclone, causing a grand spiral of wind. There are also anticyclones, which basically do the opposite. They're spiraled down from the areas filled with thinner air and simply fan out on the surface of the Earth. The way I imagined this was basically just surrounding, like something liquid, like water maybe, and pushing it upwards, and you get a splash in upwards, or an anticyclone would just be forcing water downwards. Something that can move around like fluid. The Coriolis force governs both gases and liquids, and it forces them to rotate in certain patterns based on which hemisphere the mass is in. The Coriolis force causes the winds not only to rotate north and south due to the general changes in temperature as discussed before, but it also allows them to rotate in easterly and westerly directions. Friction with the Earth's surface affects only the wind in the lower levels of the troposphere and generally slows it down. In the higher levels where there's no such friction, jet streams are formed, wind rivers that can reach speeds up to 322 kilometers per hour. So obviously these winds are not affected by the friction of the Earth's surface, and hence that's the reason they travel faster. Now let's discuss rainy weather. The atmosphere also participates in the hydrologic cycle. As water evaporates, it joins the atmosphere in the form of water vapor. Local atmospheres may contain as much as 4% water, or in more arid climates, no water at all. Water then descends back to Earth in the form of precipitation once it, evaporates up there. It does so from clouds. Clouds are formed when condensation nuclei, particles from volcanic eruption, dust storms, fires, and pollution, accumulate and condense the water vapor around them. Due to wind, these clouds can manage to stay afloat, but as the temperature drops and more water keeps condensing, it eventually results in some form of precipitation, which can be rain, hail, a lot of other forms as well. So how does wind deal with clouds? Well, there are 4 basic processes. Orthographic lifting is when airflow encounters elected terrain. My mistake there is supposed to be elevated terrain, so excuse me for that. So this basically elevated terrain is forcing the clouds upwards, and hence grouping it with less dense air. This results in further condensation and in turn precipitation. So just imagine an incline, and this air mass simply just goes up the incline. The further up it goes, well, then it goes to the less dense air, and where it's surrounded by this less dense air, it condenses into the form of clouds, and then it precipitates. This also causes a drop in temperature, and, well, you can see how the precipitation follows along with that. Frontal wedging occurs when cold and warm air slam into each other, forcing the warm, less dense air to ride up on the cloud, more dense air that forms the wedge-like shape. This generates rain clouds given that the warm air contains some water vapor. So the warm air that is elevated or propelled upwards because of the cold air, if it contains some water, it can condense and once again form clouds. As you can see, with all these different processes, we're still going to the end result of forming clouds. Convergence will have the same result. It's basically 2 different air masses of the same temperature colliding, and this simply results in both of them being propelled upwards. So it's kind of like frontal wedging, it's just different, or symmetric, I suppose. And finally, there is localized convective lifting, which functions much like a cyclone, whereas simply moves up as it gets warmer, while the surrounding air stays the same temperature. So this can happen kind of like cyclones, as in other air surrounds this hotter air, like colder air surrounds hotter air, and just forces it upwards. Not like a wedge, but more like a cyclone that we just discussed. So yeah, thank you for listening. That was all. Here are the references. I used a single slide for this because, well, it had all the stuff I needed, and it's a really good site, and it was described scientifically, and it's a scholarly source. Here are my picture sources. Wait for the clouds to pass by to see them. Yep, so these clouds there, you can see white cloud PNG images from this source and that from this source and so on. The sound effects are from Final Cut Pro X Pack. And that is the end. Thank you for listening and have a nice day.